Hi, everyone, and thanks for joining this session today on protecting your data from tampering using Azure SQL Database Ledger. My name is Jason Anderson. I'm a principal PM on the Azure Data team. And over the past few years, I've really focused on really this concept or topic of digital trust. Back in 2018, I led the effort to bring forward a new Azure service called Azure Blockchain Service, bringing managed enterprise blockchain into Azure, and spent a lot of time talking with customers about how they achieve digital trust in multi-party business processes. In this team, what I'm working on now is how we bring that into the database world and how we establish digital trust where you don't have a fundamentally decentralized model for your application. So we're going to go ahead and dive right into it. So first of all, what is data tampering? Well, I think it's pretty straightforward. It's unauthorized data modifications made to your database. Now, this can be done by authorized users, database administrators, or external attackers, malware, etc. Now, the problem with data tampering today in your database is how do you even know when it's occurred? Now, certainly we have audit logs, which can help identify patterns, unauthorized logins, etc., that will give you some context around potential tampering that may have occurred. But how do you know what has changed? Or even if you've identified what's changed in the database, how do you know what the previous values were that it should have been? Well, temporal tables provide a lot of that value by capturing the history of the rows that are modified inside of a database. The challenge with temporal is if, from an attacker's perspective, not only could I modify the main table data itself, but I could also modify the temporal tables. So I could still lose that context. So most importantly, if tampering is detected, what you really want to do is you want to remediate it. You want to get the data back into the state that you intended it to be. This typically revolves around a costly manual process of forensics to be able to determine what has happened, and then being able to remediate or restore that data back would require restoring a database to another instance and then finding those data elements that you wanted to bring back. It's not an easy thing to recover from. Now, blockchain has really opened the door to digital trust in the enterprise ecosystem. Enterprises early on identified blockchain as a utility technology to provide the ability to not only share data with multiple parties, but to ensure that that data itself is protected and cryptographically encoded on the blockchain itself. And so really what they've looked at is how can this new technology be used to ensure that in these multi-party processes, or even in processes inside of my company itself, that my data is being protected. Now, blockchain is growing dramatically as a result of the benefits that are afforded by the cryptographic methods that exist in the technology itself. Even during a year of a pandemic, we see that growth was dramatic and has a 5-year cumulated annual growth rate of 48%. So we're looking at $19 billion being spent on enterprise blockchain by 2024. So that's fantastic growth, and it will continue to move forward in that sense. But the challenge really with blockchain is it's designed for multi-party processes where trust is low or does not exist between parties inside of that network. By using mechanisms such as consensus to be able to commit data to the chain itself really impacts the throughput of being able to commit transactions to the blockchain. The governance associated with managing a blockchain infrastructure is challenging. All parties need a host infrastructure as well. And of course, writing applications that interface with the blockchain is still relatively new. And so the development tools are building, but there's not a very large set of developers that exist in the world that are adept at building enterprise blockchain-based applications. So blockchain is a challenging solution to be able to achieve digital trust. Especially when you have a system that is fundamentally centralized in and of itself, which is what most SQL database systems are today. A centralized database where other parties may interface with, but there's a level of trust between those parties that data itself is indeed intact. But adding a level of verification of that trust is really what's of interest here. Now, to that point, blockchain as a core technology can solve a lot of these problems, but why not do it in a database? So Azure SQL Database Ledger is really about bringing the power of that blockchain data structure into SQL while preserving the simplicity, performance, all of the things that you know about SQL that you love today. What we're doing is we're making data inside of SQL tamper evident using the same cryptographic patterns that exist in blockchain technology today. In addition, we provide a protected historical record of all of those changes. So a blockchain is a data pattern that only accepts inserts into the blockchain. There are no updates and deletes on a blockchain. It's an append-only ledger. With Azure SQL Database Ledger, we support that append-only model, but also support the existing model that exists today for most applications, which are complete update, insert, delete models, while still preserving and protecting that data. Now, in addition to that, the ability to externally provide proofs to other parties that that data has not been tampered with is a function of Azure SQL Database Ledger that is super important when you think about auditing scenarios. And we'll walk through some of these. And then lastly, and really most importantly, is Ledger is a feature of SQL, which means it's the same SQL that you already know today, no changes to your applications, no migration of data, of having to move to a net new technology or service. Starting with Azure SQL Database, which is where it's at today in preview, and will accrue across the SQL properties over time. So now why don't we dive in a little bit and talk about how Azure SQL Database Ledger works. Now, as I talked about before, there are two patterns that we support, an updatable and an append-only pattern. Let's start with the updatable pattern as an example. Let's say that I send a transaction to the database that impacts multiple rows. Could be a single row, but let's say it's multiple rows in this case. All of the rows that are updated or deleted in that transaction are moved to a history table. Now, you might say to yourself, well, that sounds a lot like temporal, and in fact it is. It's an extension of temporal functionality. So we capture that previous history, but in addition, we add some metadata columns to the tables, to the updatable ledger table and the history table that provide data for forensics and lineage tracking purposes. For example, we provide a transaction ID, so you know what the transaction was that made the change to those data elements in your table. Now finally, we construct a view, what we call the ledger view, which is a chronicle of your database. This will show you, here's the current value of said row, and here are the previous values and the transactions that made those changes over time. Now everything we've talked about here is really about historical record tracking changes, as well as the forensics that are associated with it. Now the blockchain layer, if you will, so we call the database ledger, is using the same cryptographic patterns that a blockchain employs. So let's dive in a little bit and talk about how that works. First of all, we're going to do a quick primer on cryptographic hashing. Cryptographic hashing algorithms such as SHA-256 take an input that could be any size, run it through a cryptographic hash function, which then produces a digest or a hash, a set of data that represents the input. It's considered a one-way hash function because that digest, that hash itself, cannot be used to derive the value of the input, but is used to verify that that input is correct. So for example, simple input here of the word fox produces a fixed length digest. If I increase the size of that input, the red fox jumps over the blue dog, the digest, the hash itself, is the same fixed size, but as you can see is completely different than the original input of fox. Now let's say that I just change a single letter in the sentence here, in this case the V and over to a U, and you'll see that the output, the digest, is completely different than the previous digest, and so on and so forth. So what we're doing in Azure SQL Database Ledger to protect the data inside of the rows themselves and the transactions is, in a transaction, as the example that I gave before, let's say where there were multiple rows that were updated, we cryptographically hash each row inside of that transaction that's been updated or inserted. In this case, you'll see that there's an example, the input being data from the row itself, producing a hash for each row that exists. We then use what's called a Merkle tree data structure to then hash those individual rows hashes together to ultimately end up with what's called a root hash. The root hash at this point now represents all of the data that's inside of that transaction, all of the rows that have been updated in a single hash entry. Now, we create blocks inside of Azure SQL Database ledgers similar to a blockchain that represent those changes. Now, I just gave an example of an individual transaction and the rows being hashed inside of it. A block will contain multiple transactions. Blocks are produced on a fixed period of time, every 30 seconds. So inside of a block, there could be thousands of transactions that have occurred. So we apply the same Merkle tree data structure and hashing to the transactions, using as input the transaction ID, the user identity, so you know who made that change, commit timestamp, and then the root hash from all of the rows that inside of that particular transaction itself. And then again, using a Merkle tree data structure, we end up with a root hash for the block. So now that the block has a root hash, we then again cryptographically hash that root hash with the hash of the previously published block together to create a hash for that particular block. This chains them together in the exact same pattern that you would see in a blockchain such as Ethereum, for example. Now, these root hashes that represent the block are considered the cryptographic proof of the data state at that point in time that the block was produced. We call that the database digest. Now, the database digest, once it's created for each block, is pushed externally outside of the SQL server into a trusted storage location. Now, a trusted storage location could be Azure Immutable Blobs with a locked and configured immutability policy. It could be Azure Confidential Ledger, which is another blockchain-based service for file storage. Or it could be your own on-premises worm device or any location that you choose. The important piece here is that storage location must be protected from tampering, as those digests contain the state of the database at the time the blocks were produced. This is important because as we go to the next step, which is verifying the database, detecting if any tampering has occurred, when we run the verification process, meaning the user that's using the database themselves, or it could be an external party, such as an auditor or a regulator runs the verification process, which effectively kicks off a stored procedure that references the database digest stored in trusted storage. We then recalculate all of the hashes inside of the database during verification and to see what the results are and compare them to the database digests that are stored in trusted storage. If those hashes don't match during that verification process, then we know a tampering event's occurred, and we have the data lineage information to know where it's occurred, and most importantly, the historical context around what has changed. Now, append-only ledger tables work the exact same way that a updatable ledger table works at the cryptographic blockchain level. The only difference is updates and deletes are blocked at the API layer. This avoids a database administrator from doing malicious updates and deletes inside of the database. The SQL server itself will reject any update or delete statement. Outside of that, it's the exact same. As you can see, there's no need for a history table in this case because it is an append-only pattern, so the append-only ledger table has that chronicle version of the database. So now let's jump over and take a look at a demo practically and how it works. We'll start with the configuration of SQL Database Ledger, which can be done during the create process of a SQL database. So as I create a SQL database, what I can do here is as I go to the next steps in the create process, you'll see that there in the security tab, there's a new feature called Ledger. And in Ledger, you have the ability to then configure the ledger itself. So let's talk about the configuration options that exist inside of this pane. First, we offer the ability to make the database itself ledger enabled. This means if I click this box, that every table created inside of the database going forward will be automatically an updatable ledger table. This is the easy button to ledgerize a database. Now, if I wanted to have a database that had a mix of updatable ledger tables, append-only ledger tables, or non-ledger tables, I could uncheck this. I don't need to have that. This is just to make it an easy button to make them all updatable if you'd like to do that. Now, the important element here is the digest storage, where those cryptographic hashes, those database digests, are stored. So we automatically set up the ability to configure it against Azure Storage or Azure Confidential Ledger. And when you do it against Azure Storage, we'll automatically configure a storage account, or you can choose an existing one, but the storage account that you choose must support the properties that are necessary to support immutability policies. Since we can't configure the immutability policy completely in the Azure portal, you'd have to do it after the fact, but at least the container will support that so you can then configure it. Now, Azure Confidential Ledger is an enclave-backed storage service that uses secure enclaves and the Confidential Consortium framework to provide a truly immutable storage service that even removes Microsoft outside of the trust boundary of that service. Azure Confidential Ledger is also in public preview right now, such as just like Azure SQL Database Ledger is. During preview, there's no charge for it, but there will be a charge when it goes to GA. It's important to note that Azure SQL Database Ledger, there are no additional charges to use this capability. So once I've configured that, and once the database has been provisioned, you'll see that in the security pane inside of the Manage experience, there is now a Ledger option. And you effectively have the same configuration experience that we just showed in the Create experience. Now, one of the primary differences here is if I had checked this checkbox during the Create statement, or during the Create process, I would not be able to disable this later. Once a ledger table in general has been created, it cannot be turned off and made an unledger table. That's primarily for security reasons. It'd be very easy for a malicious user to turn ledger off on a table, make the malicious changes they wanted, and then turn it back on. So by making this a one-way switch, either at the database level here, or specifically when you create a ledger table itself, which I'll show an example of, it's a one-way function. Now, I can change the digest storage location over the lifetime of this running database. If I started with Azure Storage and I had it running for a while, it's been producing digests, but I decided, hey, I want a higher security boundary. I want to choose Azure Confidential Ledger. I'd be able to change that and create an Azure Confidential Ledger, and then digests would start to be stored there in the future. But the system configures it such that the context of all these previous storage locations for the digest are all orchestrated in the verification experience, which I'll show in just a minute. But first, let's go ahead and let's take a look at the data elements of actually creating ledger tables. So as you can see here, I'm already connected to a database that doesn't have any tables in it at this point. So let's go ahead and create a very simple banking schema. What we're going to do here is we're going to just have a customer ID, which is the primary key, first and last name of the customer in the bank, and their balance. Now, this database is not a ledger database, so by specifying the ledger equals on statement, this will make this table an updatable ledger table. If I wanted it to be an append-only ledger table, I would add in addition to here append-only equals on. Well, let's go ahead and run this and create the schema. Okay. So as we can see now, our table should show that we have this table created. Okay, we can see that that table has been created. Not only has the account balance table been created, but you'll see that the history table has been automatically created for you. Okay. So now let's go ahead and let's start inserting some data into the database. So let's insert our first customer, Nick. And we're going to give Nick an initial balance of $50. So let's go ahead and run this statement. Okay, fantastic. So Nick is there. Now, as we can see, if I take a look at my account balance table, we see Nick is there with $50. Pretty simple and straightforward. But now let's go ahead and let's add another transaction here. What we're going to do now is we're going to add a transaction that inserts multiple customers. So we're going to insert John, Joe, and Mary with varying balances into the database. So let's run that value now. Okay, so that's completed. So now that we have multiple entries in the database, what will be interesting to show now is to look at the ledger view. So let's take a look at the ledger view. What this will give me now is a view of all the data elements, but also some interesting information around that forensics and tracking. So you'll see here that we have a ledger transaction ID. This is the transaction ID associated with the transaction that we just ran. So Nick had a single transaction, so his transaction ID is 1453. But that second transaction we ran that inserted John, Joe, and Mary have the same transaction ID because they're a part of a single transaction. Now, if I go to the ledger sequence number, you can see the order of operations that transaction happened. So you can see when those happen in the context of that transaction. So that's an important element to understand. We also see the what type of operation happened. And in this case, it's been all insert. So let's go ahead and do some more changes here. Let's go ahead and let's update Nick's balance now. Change it from $50 to $100. Okay, so now let's go back. Let's take a look at our ledger view again here, and we're going to see some. We're going to see the changes that happened to Nick. So we see Nick here has a balance of $100 as expected. In addition to that, he has a new transaction ID that was initiated by that latest transaction that we ran. But we still see the history here. So here's Nick Jones' original balance of $50, but we see it twice. So we see it in the context of the original transaction, which was an insert, followed by a delete. So what happened was when we updated Nick's balance from $50 to $100, we actually deleted that entry from the updatable ledger table. We inserted it into the history table, and then we inserted a new row of $100. So this gives you a view of the high-level telemetry or the high-level forensics and data tracking that's associated with ledger tables. So now that we've made these changes, now we're interested in how do we verify the database itself has been not tampered with. So let's go back and take a look at the Azure portal. Now inside of the Azure portal, this is the same database that I was just in. So if I go to verify database, what this is going to do, it's going to pre-populate the T-SQL needed to validate the database or verify the database. I'm going to copy this to my clipboard. And now we'll switch over to Azure Data Studio and let's paste that in. Now let's take a look at what we're doing here. What we're doing is we're effectively fetching the location of where the ledger digests exist, or the locations of the digest. We're then running the verification stored procedure, passing in the digest locations. So in the event that I had multiple locations, they'd show up. In this case, we only have one, but let's run this. And let's take a look at what our results are here. We get two sets of results. One, we get ledger verification succeeded. And that will tell you specifically that the ledger has been verified up to block 3. Now, why block 3? So we had 3 transactions that have happened here all up. We inserted Nick, we then inserted multiple customers, and then we updated Nick. So every time that happened, we had a new block because it happened within, each of those transactions happened within a 30-second period of one another. Now, the second thing we see is the digest locations. So let's open that up. And while this just shows the one location, it's showing that location. And this is important because an advanced attacker could try to forge the digest and point it to a different location, different storage location. And so we want to make sure that the location that you expect is listed here, that it's run against. And then this is current true is showing that this is the currently configured digest location. If there were previous locations that you had that were configured but you switched to a different location, those previous locations would show as false. So that's a quick view of how to validate, verify the database itself for integrity. So now that we've seen how the data elements work inside of the database, let's switch gears and let's show you a real application running SQL Ledger, specifically a demo of protecting HR data. I'm going to turn it over to my colleague Jacob Samasket, who will take it away.
For this demo, I'm using a human resources application that allows me to view and manage employee records. This application talks to a database in Azure SQL DB, and here I'm connected to the database as a DBA. I can view employee records. One thing to note here is that two columns in the table containing employee information, SSN and salary, are protected with another security technology called Always Encrypted, which helps prevent data exfiltration by malicious operators and administrators. So the DBA cannot see or steal sensitive data stored in these two columns. However, he could attempt to tamper with that data. Let's say the DBA is Jay Adams, who is also an employee in this organization, and Jay wants to maliciously give himself a salary raise by updating the value of his record in the salary column in his record. Well, because the salary column is encrypted, this makes things slightly more difficult for Jay. Namely, he cannot insert an arbitrary value into the salary column. However, he could, knowing that, let's say, another employee, Catherine, holds a higher level position, Jay assumes that Catherine likely makes more money than he does. Therefore, he decides to replace his salary with Catherine's salary by running a T-SQL update statement against the database. So now, as the statement completed, Jay is hoping to receive a nice higher paycheck in the next payment period. However, unfortunately for Jay, this application is protected with this database. This dataset is protected with the ledger technology. The employee table is a ledger table in which both the current and historical data is tamper evident and is cryptographically verifiable. Let's see how that helps to streamline and automate the audit process. Let's assume a few days later, an auditor, Alice, comes to this application and runs her routine review, her routine audit of changes into the HR system by starting the ledger verification process, by kicking off ledger verification. What it does, it cryptographically, mathematically verifies the data the auditor is going to review subsequently is genuine and can be trusted. So in the next step, the auditor looks at the history of changes that has been automatically captured by the ledger feature for the employee table, and in that history historical view of the changes, the auditor clearly sees that at some point Jay's salary was updated, and it was Jay who actually made this change. And because the ledger data structures has been cryptographically, mathematically verified as genuine, Jay cannot be effective in denying that he was the person who actually has made this change. So this illustrates the key benefit of the ledger technology, which is ensuring non-repudiation, and it also shows how ledger helps streamline, automate the auditing process.
Thanks, Jacob. So let's take a look at some of the core scenarios that we see where ledger tables can really help establish that digital trust. The first one is streamlining any audit process that you may have inside of your business today. This could be an internal process to verify that internal systems have not been modified by company employees. It could be external audit verification for regulators, external auditors that might look at your records for tax purposes, accounting purposes, etc. Any data that you have that is production data that you rely on your business to execute upon should be protected in this sense to ensure that it's not been tampered with. The second has to do with multi-party business processes, and this is really tied to the scenarios that we talked about earlier with regards to blockchain. Many customers that are going to blockchain are doing so under the guise that blockchain is the only way to achieve digital trust. Prior to working on Azure SQL Database Ledger, I used to lead Azure Blockchain Service. So I spent time talking with hundreds of customers that were looking at use cases that they thought they had for blockchain. And in many cases, when we would evaluate their use cases and look, we'd say, you know, blockchain is really too much. It's too heavy for what you need. You have a fundamentally centralized system. Or They don't have the need for the smart contracts that are encoded in the blockchain. They don't have need for tokenization. Blockchain offers a lot of utility, but if really what you're trying to achieve is data protection and attesting for that data protection to other parties, blockchain is a heavyweight solution. So we're finding that many customers that are looking at blockchain are now coming to Azure SQL Database Ledger, and I'll show in a couple examples of those in a second. The core difference, again, between looking at a blockchain-based solution or an Azure SQL Database Ledger solution, again, is that, is it a truly decentralized process that you need to build trust, or is it a centralized one where you want to trust but verify? Now, another connection to blockchain here is what's called the trusted off-chain store. And so what I mean by that is blockchain systems that are in place today are notoriously challenging to be able to query. Again, the throughput issues that I talked about earlier, fundamentally the databases that back traditional blockchains are not OLTP-based systems. They're not optimized for high throughput query. So if you wanted to analyze ledger data on the blockchain from a year ago, 2 years ago, doing so is very taxing on the node, and it's very challenging. There aren't a lot of applications and systems that integrate directly with the blockchain. So a pattern that we saw and continue to see with blockchain-based implementations is taking the data that's on the blockchain and copying it off onto an off-chain store, such as a database. Then you're able to plug in the tools and development components that already exist today, such as Power BI, all the analytics services that exist. It's much easier today, or it's a much more mature ecosystem to integrate in with, for example, SQL Database than it would be into a bespoke blockchain node. Now, the problem with that off-chain store, up to the point that we have SQL Database Ledger now, was that off-chain store was not secure. You lose integrity as soon as you copy it off of the blockchain to a different location. How do you maintain that that data is still representing the blockchain? So pairing an Azure SQL Database Ledger with an existing blockchain-based solution maintains that level of integrity from on-chain to off-chain. So some of the customers and partners that we've worked with. Let's start in the middle with Avanade. So Avanade is a partner that has a long history working with Microsoft. They realized the power that Azure SQL Database Ledger can bring to digitally transform a lot of business opportunities, and have actually built a practice around this, and specifically have stood up a GitHub repo with some samples and example applications. And so we work closely with them and other customers to drive this digital transformation into their existing SQL systems or into blockchain systems that want to pivot over to a database-based system. British Petroleum is a good example of using blockchain as an off-chain store. They are building a blockchain-based solution for gas and oil derivatives trading, and needed to have the ability to have not only an off-chain store, but what they found is the ability to integrate with SQL to run their business logic that's syncing from the blockchain was a lot easier than integrating directly with the blockchain. And then lastly, RTGS Global, which is a close company to Microsoft. RTGS Global is working on building a liquidity network for banks. And what this means is banks that exist in different countries that have to manage transfers between one another of different currencies need to be able to do so quickly. And today, the process that exists can take hours, if not days, to be able to complete. A blockchain wasn't a good solution for them because of the data residency requirements that exist inside of these countries for ledgers of banking transfers. They needed to be able to have a system that could be geo-fenced to particular countries or even geos. And so by using Azure SQL Database Ledger as the core ledger of those liquidity transfers, not only did it eliminate the overhead of a blockchain, but gave them easy integration of the system, as well as that political boundary or the geographic boundary they needed to keep that data safe. So if you're interested in learning more, a few resources here. The first, the white paper, this is really a deep dive into how the cryptographic elements work inside of Azure SQL Database Ledger. So this is really if you want to geek out and understand Merkle trees and data structures at that level, this is a great download to look at. The Announce blog talks a lot about some of the customer scenarios we just talked about. Documentation, of course. And if you look at the documentation, you'll find some tutorials that map the scenario that I just talked about. So you yourself can walk through and try these samples yourself and see how that data lineage works. There's a link here to the Avanade blog and their GitHub repo for their sample application, and the case study for RTGS Global is live, and you can look at that link here. So with that, thank you for attending, and look forward to your questions and partnership going forward.